All right, we're back. We're on page 4 of notes 13 from Calc AB. We're talking about antiderivatives. It's a skill. You develop the skill. Like, it reminds me of like when people were learning to factor and they're like, factoring's impossible. Like, antiderivatives, I will straight up tell you, they're more complicated than derivatives because it's like less obvious what to do. Derivatives, there's a fixed number of rules. You recognize the type of function, you apply the rule. Antiderivatives, it's more like it's an art more than just a direct application. But through practice, you will get good at it. And that's the key thing to keep in mind. So here are some that you need to have memorized, because if you have them memorized, a lot of things look like them. And then you kind of know where to go with your u substitution, etc. So let's see if we have these memorized. This is just going to be 1 over n plus 1, x to the n plus 1, n not equal to -1, I guess. That's reversing the power rule. Ooh, plus c. Where do you put plus c in this scenario? I guess I put it like here. And then I say n can't be -1 to begin with. I guess. Yeah, I mean, all right. This is the scenario where n is -1. So this is going to be the natural log of the absolute value of x. And that's a domain thing, right? Domain of this is everything except 0. The domain of natural log of x would be x greater than 0. But this, I can plug any value other than 0 in and take the natural log. So we fixed the problem by putting the absolute value, and you're going to do that with natural logs pretty much all the time. You throw in an absolute value. I would say like 99% of the time that's the right thing to do. Sometimes you can get rid of it because the thing itself is always positive, but if you can't, leaving it doesn't really hurt. So, do it. E to the x is the derivative of e to the x. That's super good to know. A to the x. This is one you really have to have it memorized, right? The derivative of a to the x is a to the x natural log of a. So if there is no natural log of a, I need to like put it in with my u substitution. So this is going to be 1 over the natural log of a times a to the x plus c. I would say this one, like people forget it. It doesn't come up often enough for it to be like burned into your brain. So review that one every once in a while. I don't know. Note cards, probably the ideal thing to do. The derivative of sine is cosine. So that's like really how I work these out, is I look at it and I think like, what's that the derivative of? I don't really think what's the antiderivative of this. Like the derivative of cosine is negative sine. So this should be negative cosine. Secant tan. So the derivative of secant is secant tan. So this one works out kind of perfectly. Plus c. So we have that like co-function thing going on, right? Like the derivative of sine is cosine, the antiderivative of cosine is positive sine. The derivative of cosine is negative sine. The antiderivative of positive sine is negative cosine. It's like it picked up a negative. The derivative of cosecant is negative cosecant cotan. So here, this is not negative, so I need to balance that out. So this should be negative cosecant. And then you're probably maybe hopefully starting to notice you get that co thing again. It's like with normal functions, every time you take a derivative of a co-function, you pick up a negative. Cosine is negative sine, cosecant is negative cosecant cotan, cotan is negative cosecant squared. The derivative of every co-function is a negative something. Here, every antiderivative that's leading to a co-function picks up a negative. So the derivative of tangent is secant squared. So this is tangent. So the antiderivative of cosecant squared should be negative cotangent, because the derivative of cotangent is negative cosecant squared, so we got to balance out that negative. And then this, if you recognize it, you're good. If you don't, you're in trouble, because there's not much you can do when you don't remember it. This is the derivative of arc sine. And this is like a really, really common function to work with. It's actually the derivative of arctan. See, so these are the ones you have to have memorized, because if you have them memorized, memorize them right now, like get them done. If you have them memorized, your u substitutions can go somewhere. If you don't have them memorized, you're like a little bit lost, and it's like a bad place to be. So make sure you memorize those. They're going to show up all over the place. Now let's do two problems that are like almost completely unrelated to those. But it's like, these are a demonstration of how like weird antiderivatives can be, how crafty you got to be sometimes. So if I want to integrate tangent, I have no idea how to do that. Sort of. I actually have two ideas of how to do that. The first one is the one that I think most people would go with. Tangent is sine over cosine. So I'm just going to do that. And now I need to make a choice of u. So I look at this thing and I say, there's not really an obvious choice, but there's a fraction, and sometimes the denominator works. So I'm going to say that u is equal to cosine. Then du, the derivative of cosine, is negative sine of x dx. So it's not quite right? It's supposed to be negative du is sine of x dx. So this I can turn into negative du over u. And that's one where it's like, it's u to the negative first. So we don't reverse the power rule. We say that's natural log. So this is negative natural log. We put in the absolute value to fix the domain issues we might run into, plus c. And then negative natural log. Absolute value of u is actually cosine. Whoops. Let me fix that up. Plus c. Okay, and you could leave it that way. Or you can say that the negative that's sitting out here is actually the exponent of the thing inside. So you could say this is natural log of the absolute value of cosine of x to the negative first, right? That's because coefficients become exponents. And then 1 over cosine is actually secant. So there's many ways that you can write this. Let me show you a slightly different way to do this. I saw it for the first time in my life this past year. One of my students actually was like, couldn't we have done blah, blah, blah? The thing I'm about to do. So if we want to integrate tangent, so like start going through your list of the derivatives of the trig functions. You got sine gives you cosine, cosine gives you negative sine. Secant gives you secant tan. That's interesting because it has a tangent in it. Cosecant gives you negative cosecant cotan. Tangent gives you secant squared. So the only one that actually had a tangent in it was secant. The derivative of secant was secant tan. Well, we have a tangent. How do we get a secant tangent? So to get that, I'm going to multiply by a very clever form of 1 inside of the integral. So you're only allowed to do this inside the integral because of the x. But this is equivalent, right? Just cancel the secants and you're back to the original. Now what if you let u equal secant of x? Then du is secant of x tan of x dx. It's perfect. This is the integral of du over u, which is a natural log of the absolute value of secant of x plus c. I had never seen that before. And one of my students showed me that this year, and I was like, that's awesome. And I'm going to try to remember that. And I did. It's a little easier. It's a little more direct to get to the secant type answer. But again, you got to be that clever problem solver to think like, let me just run through the derivatives that I know and see if anything comes up. So like I don't know how likely that is to happen. But once you see it, cool, very cool. All right, and then we have the integral of secant. I don't know. I know the trick for it. I don't know a trick for like working out where this came from. My thought is that somebody took the derivative of the antiderivative of this at some point and like simplified it to secant. And they're like, whoa. So here's the trick. It's another clever form of 1 type thing. We got secant. I'm going to multiply by, and there's a reason for this, and you'll see it. I'm going to multiply by secant plus tan over secant plus tan. So antiderivatives of powers of, oh, that's not a u. Antiderivatives of powers of secant is like a thing. And they're all kind of weird, and they're all like sort of like secant cubed. At some point, you're not ready for it. At some point when you're ready for it, the integral of secant cubed is like the hardest easy integral in the world. Like it's the dividing line between easy integrals and hard integrals. It's got a lot going on. And this is just the integral of secant. It kind of has a lot going on. Secant squared, secant tan, and over secant plus tan. All right, now why does this work? This works because the derivative of secant is secant tan, and the derivative of tangent is secant squared. So if I make u equal secant of x plus tan of x, what's going to happen? Well, when I find du, I'm going to get the derivative of secant is secant tan. The derivative of tangent is secant squared. And then dx, because it's differential. So this is now just, whoa, du over u, which is natural log of the absolute value to fixed domain issues of u plus c. And then u is secant x plus tan x. Natural log, absolute value. This one comes up surprisingly often. I mean, like the fact that it ever comes up, I think, would make it surprising. And then the fact that it's like, it's not uncommon, like it will come up. The antiderivative of secant is the natural log of the absolute value of secant x plus tan x plus c. Crazy. All right, so these are things you need to memorize for sure. A technique that is worth memorizing or being aware of. Rewrite using trig identities, that kind of thing. Or be super, super clever, which is great, but you can't like bottle that being super, super clever. Multiplying by clever form of 1, though, is a pretty good way to go. Did it here, did it here. It works out. So this one, I would say, like, definitely like back in the back of your head. Keep that in mind. So I'll be back in the next video. We'll do more. Make sure you memorize all those antiderivatives. They're what make u substitutions really work for you after you've done the substitution. And if you can't do the substitution and get something you can work with, then what's the point of the substitution? So anyway, I will see you in the next one.